Hi, when it comes to that of signals and systems and in Fourier series, there is an important topic, establishing relationship between the coefficients dn and cn. So if you know previously the expressions for dn and cn, straight away you can establish that. But exam point of view, you'll have to derive from the trigonometric Fourier series. So let's check if where it starts from. The story starts from that x of t will be equal to a naught plus summation n equal to 1 to infinity an cos n omega naught t plus another summation for my convenience. All right, so to prove this, it will be convenient if we derive the expression for cn on one half and dn on either another half, and then we can establish some relationship between that two. So another one, so summation n equal to 1 to infinity bn sine n omega naught t will be the trigonometric Fourier series expansion for any given signal x of t. Approximation it's all about. And according to Euler's identity, cos theta can be written as e raised to j theta plus e raised to minus j theta by 2, isn't it? And sine theta can be written as e raised to j theta minus e raised to minus j theta by 2j according to Euler's identity. And comparing over here, theta is n omega naught t over here. All right, so let me, to save time, let me write it over here itself. This is our theta, cos theta, entire this thing is our theta. So plugging in that over here according to Euler's identity, let me not rewrite it again. All right, so cos theta, cos n omega naught t is equal to e raised to j n omega naught t plus e raised to minus j n omega naught t for cos n omega naught t theta. And over here once again n omega naught t over here, sin n omega naught t, once again n omega naught t over here, and even this is n omega naught t. So plugging in this back to over here, so this takes the transformation x of t will be equal to a naught as it is, a suffix o as it is, summation n equal to 1 to infinity a n is also as it is, and in terms of cos we're going to plug in this Euler's identity. All right, so that will be taking e raised to j n omega naught t by 2 plus e raised to negative j n omega naught t by 2. All right, for my convenience, for backbenchers, to be easy for backbenchers, plus n equal to 1 to infinity bn also as it is from here, and this entire sign term in terms of Euler's identity, it will be e raised to j n omega naught t by 2j in the bracket minus e raised to minus j n omega naught t by 2j, close the bracket. All right, soon after this a0 a naught will be continuing as it is, and taking out, guys, summation plus it's a summation. All right, so summation n equal to 1 to infinity, guys, e raised to positive j n omega naught t as common from here and here. All right, so what it is, taking out for the first time, for the first term, e raised to positive e raised to j n omega naught t as common from here and here. So what do we have? It's a an by 2, all right, plus bn by 2j from here. An by 2 will be over here, because this is written over here. All right, even this is written over here. So from, in that case, an by 2 over here and bn by 2j over here. All right, and from the second term, from the second summation, n equal to 1 to infinity, not from the second summation but as a common from here and here, taking out e raised to negative j n omega naught t as common from here and here. So what is left over? If this comes out, an by 2 an by 2 is left over, and from here negative bn by 2j, negative bn by 2j is left over here. Alright, and 1 by j can be written as negative j. 1 by j will be equal to minus j. Making use of this transformation, here we have j over here. I'm taking it to the numerator. Check, here we have a j over here. This, taking it to the numerator, it will be minus j bn, and over here even this will be carrying a negative to the numerator. That negative and this negative, that becomes positive, and we don't have this j anymore, so this is our j over here. Alright, now this can be totally written as an minus j bn upon 2, only single 2 common, alright, by 2. Alright, so even this one by 2. Well, what do we have? Here we have negative, here we have positive. Alright, so guys, a0 as it is plus summation, guys, this one, n equal to 1 to infinity, this entire thing, this entire in the brackets, it's considered to be c suffix n, an minus jbn by 2, entirely this inside the bracket is considered as negative cn into e raised to jn omega naught t as it is. Alright, plus summation n equal to 1 to infinity. Alright, and guys, here hold on just a few seconds. an minus jbn by 2 is taken as c of n, c suffix n. Now this is, can you see clearly, it's this is the complex conjugate of this one, an minus jbn. Here we have an plus jbn, so this will be, now this is the complex conjugate, conjugate of this one, so it is written as cn is the conjugate of cn. Alright, so this is what, into e raised to negative jn omega naught t as it is. Alright, so there is a hidden cn over here. I need this place to continue. In that expression, the final expression, even the second term, third term, we have the second term hidden somehow, some transformation it is. All right, so guys, we have we can prove that from the trigonometric Fourier series, exponential Fourier series. Like when we were approximating signals, we had an expression c of n is equal to 1 by t integral 0 to t x of t e raised to negative j n omega naught t. We had this evaluating the coefficient. In that case, what will be the conjugate? Cn conjugate will be equal to 1 upon t integral 0 to t x of t e raised to conjugate j n omega naught t. All right, and if we plug in negative n, from here, okay, this is the conjugate, that's okay. But if we go for this one, negative n for this very expression c of n, and if you want to extract the negative n, where do we have here n will be negative n. Here we have this one, n will be negative n, and this negative n, and this negative and this negative becomes positive, in the sense this is equal to this. This can be plugged in with this one from this discussion. All right, so in that way, x of t will be equal to a0 plus summation n equal to 1 to infinity. We have cn e raised to positive j n omega naught t as it is. All right, plus summation. What do we have in the place of this? We can plug in with this one. Where is that? N equal to 1 to infinity, and it's c negative n e raised to minus j n omega naught t. All right, j n negative, this is the one, this is the transformation which we have after considering that one. So extracting negative summation, what do we have? A naught plus summation n equal to 1 to infinity cn e raised to j n omega naught t plus summation n equal to, guys, n equal to negative summation to negative 1 c minus n e raised to j n omega naught t. All right, so extracting negative n from here, so this will be the transformation. And so we have, see, it is starting from n equal to minus infinity, n equal to minus infinity, and we also have 0, and also we have n equal to 1 to infinity. So it's a complete one summation. It's a summation from summation n equal to negative infinity to positive infinity. Even this comes inside the summation. Why? Because here also we have e raised to j0, and that is 1. All right, here also we have j0, so even this is a part of this summation. Okay, I'm sorry, I forgot to tell you, this is no more a naught over here. Once we consider this over here, this is cn, and this becomes c naught. All right, I'm sorry, I didn't give you a reminder, c naught over here, and so this will be c naught, and even here also it's a c naught. All right, so negative infinity, 0 to positive infinity, and so entirely can be closed into one summation, and c of n e raised to j n omega naught t. All right, and okay, like what was cn previously, guys? This is because to prove this one I need to have cn. This was I was trying to do for. What was cn? How was cn closed? It's a an negative j bn by 2, if I'm not wrong. This cn, the previous one. All right, so this was the transformation, isn't it? So it's right, cn is an minus j bn was that. All right, this is for the exponential Fourier series, but I wanted to have this one. With the help of this one I can prove this proof. All right, so cn. Okay, like if you are confused with this, no, I'm not focusing on this one. My intention is to prove this one. All right, so on the other hand, once again starting with the trigonometric Fourier series once again, because we need to have this one also. All right, on the other hand, once again starting with the x of t, which is equal to, again, the trigonometric Fourier series. What is that? A naught plus summation n equal to 1 to infinity an cos n omega naught t. All right, this is the one, and plus, it's not over, plus summation n equal to 1 to infinity bn sine n omega naught t. Don't bother with my script. All right, not a bad handwriting, but it's my style. That's it. All right, so this is the one. So guys, what if we have a triangular like this one? What if we have a triangular with the theta over here? What if we have an over here, the adjacent one, and bn over here? So what will be the hypotenuse? It's under root an square plus bn square, isn't it? So this will be, so to reduce this even more, there is some hidden reduction over here. So what if I multiply with an square plus bn square, and also divide with the same thing, an square plus bn square under root. In the same way with this one also, what if we do this, an square plus bn square under root an square plus bn square. All right, so gets cancelled, and we go to the previous one, isn't it? So taking out an square plus bn square as common from here, and here what will be the leftover? X of t will be a0 plus, let me write down that outside. All right, bn, no, like summation, taking out both under root an square plus bn square as common from here, and here what it will be? So taking it n equal to 1 to infinity, what do we have? Under root an square plus bn square is taken out as common from here, and what will be left over? So guys, I have taken this one to be, let me save time. All right, let me not kill much of time in the video. So it's taken out, and so this could be understood from here itself. So what is this? What is this? That can be written as cos theta from here itself. Cos theta over here, it's adjacent by hypotenuse, isn't it? From a triangle, if we could construct with the same values, if we have a triangle, that can be reflected over here, that reflects over here. So an adjacent by hypotenuse, it's cos theta, isn't it? Cos theta from this one, cos theta, cos n omega naught t plus over here, what did we have? Yeah, bn, in the sense opposite by hypotenuse, that's sin theta, that's sin theta into sin n omega naught t. So guys, can you see this? Cos A, cos B plus sin A, sin B. So even more from the trigonometric relationships, that can be written as a naught plus summation n equal to 1 to infinity, what do we have, under root an square plus bn square over here, and this could be closed as cos A, cos B. So it's n omega naught t plus theta. Alright, so this entire thing from here to here, it will be cos A plus B. Alright, and a small transformation over here, a continuation. It's a polar representation of Fourier series. It's x of t will be equal to, guys, the summation as it is, n equal to 1 to infinity. This entire thing is denoted with dn. Alright, and cos, what is that? N omega naught t plus theta. And from the triangle, you know if what is theta, it's tan inverse, negative tan inverse b by a. So that theta, my intention is to prove this one. I've got dn, and what to do with this a naught? This will be d naught. That's it. All right. So what is from here? What is dn? dn. No. What is under root a n square plus bn square? It is dn, isn't it? dn, right? On the other hand, we have cn. Cn is this. Cn, we already have this one from the previous one, cn. And what will be the modulus of cn? Cn will be under root an square plus bn square, isn't it? By 2 under root square, and we don't have this anymore. We don't have this anymore, and what it will be? Under root an square plus bn square equal to 2 times c suffix n. Because here dn is under root an square plus bn. Even this is under root an square plus bn, and so dn will be equal to 2 times of c n. So this is to be proved. Prove that it's done. Thanks for watching.